Hello, class, and welcome to Chapter 3, Section 2, Units of Measurement. So we're spending a lot of time this chapter going over significant figures, scientific notation, and this section kind of gets into units of measurement and using the standardized system of units called the SI system or the metric system. The metric units are the standards of measurements used in science, and all metric units are based on multiples of 10. Because of this, you can convert between units very easily. And I will also include another video in this module. The metric system was originally established in France in 1795, and the International System of Units, abbreviated SI, is a revised version of the metric system. The SI system was adopted by international agreement in 1960. I just got a notification that my internet is a little slow, so I'm just going to make sure everything's connected okay. Okay, so this SI system, International System of Units, is officially adopted by the International Agreement in 1960. And this is really important to have a international system of measurements worldwide to be used and accepted so that when doing research and sharing research in scientific journals, scientists are using the same units so that they could potentially recreate experiments that another scientist on the other side of the world is doing. So these are the SI base units based on quantity, the SI base unit, and then the symbol. So length is always measured in meters, abbreviated M. Mass is measured in kilograms, labeled kg. Temperature measured in Kelvin, labeled with an uppercase K. Time is measured in seconds, labeled S. The amount of a substance is a mole and measured, abbreviated MOL. And luminous intensity is the candela, abbreviated CD. And in electric current, we always measure in amperes, labeled with the uppercase. So as we move forward, there are 7 base units, and from the base units, all other SI units of measurement can be derived, and derived units are used for volume, density, pressure, and so forth. Units of length in the SI units, the basic unit of length is the meter, and for very large or very small lengths, it is better to use a prefix with the base unit of meter. And I'll show you an example of that. So for example, the base unit of the meter is right kind of in between a kilo and a deci. But if we have a megameter, that's 1,000,000 times larger than the unit it precedes: kilometer, decimeter, centimeter, millimeter, micrometer, nanometer, and picometer. So what these prefixes do is they use to describe these SI units based on the factors so much larger or so much smaller than the actual base unit. So a kilometer, for example, is 1,000 times larger than the unit it precedes. So a kilometer, kilometer, is 1,000 meters. A millimeter is 1,000 times. Okay, units of volume. So volume is the space occupied by any sample of matter. So the volume of a rectangle or a square, we always take by multiplying the length times the width times the height, and that is equal to the volume. And the unit for volume is dependent on the units of length. So for example, if we're measuring in centimeters, for example, the volume would be length times width times height, or centimeters cubed, and that gives us the volume. Units of volume, this SI unit of volume is the cubic meter, so meters cubed, and it's more convenient. The more convenient unit of volume is actually the liter. So even though we measure volume in length times width times height to get a cubed, it's actually more convenient to measure volume using the liter. And a liter is the volume of a cube that is 10 centimeters along each edge. So if we take a cube and it's 10 centimeters along the height, the width, and the length, we get 1,000 centimeters cubed, and that is equal to 1 liter. So metric units of volume and their relationship and some examples. The liter is for the liter, that's the base unit of volume, and a quart of milk is roughly 1 liter. A milliliter So 1,000 milliliters is equal to 1 liter. So 10 to the third is 1,000. That is equal to 1 liter. And about 20 drops of water is 1 milliliter. The cubic centimeter, cm cubed, 1 cubic centimeter is equal to 1 milliliter. And a cube of sugar is about the size of 1 cubic centimeter. And the microliter is even smaller. So what would this be? 1,000,000 microliters, 10 to the sixth, one with 6 zeros at the end. That's 1,000,000 microliters is equal to 1 liter. And a crystal, a teeny tiny crystal of table salt is about equal to 1 microliter. Units of mass. So the mass of an object is measured in comparison to the standard mass of 1 kilogram, which is the basic SI unit of mass. And a kilogram was originally defined as the mass of 1 liter of liquid water at 4 degrees Celsius. A gram is 1/1000th of a kilogram. So here we have a gram. The kilogram is the base unit. So 1 kilogram is equal to 1,000 grams. We have a milligram and a microgram. 1,000 milligrams is equal to 1 gram, and 1,000,000 micrograms is equal to a gram. And you have some examples here. A small textbook is about 2.5 pounds, 1 kilogram. A dollar bill is about a gram, or a paper clip is about a gram. 10 grains of salt is about 1 milligram cubed, and a particle of baking soda is 1 microgram, so incredibly lightweight. Units of mass. So weight is a force that measures the pull on a given mass by gravity, and the weight of an object can change with location. If you're on the moon, the Earth, another planet, out in space, but the mass of an object will not change with location. So our weights are determined by the force of gravity on us, and gravity is 9.8 meters per meter squared. But if we're on the moon, our weight will be different than if we're in outer space or on Earth. But the mass of our objects will never change. So the mass of our bodies will never change on location. Okay. Units of energy. So energy is the capacity to do work or to produce heat. And the SI unit of energy is the joule, named after James Prescott Joule, who was an English physicist. Units of energy. The common non-SI unit of energy is the calorie. We use that a lot in biochemistry. And 1 calorie is the quantity of heat that raises the temperature of 1 gram of pure water by 1 degrees Celsius. Units of energy. So converting between joules and calories can be carried out using the following conversion rate. So 1 joule is equal to 0.2390 calories, and 1 calorie is equal to 4.184 joules. So you can use that conversion when converting between joules and calories. Temperature scale. So temperature is a measure of how hot or cold an object is, and it determines the direction of the heat transfer. So for example, when 2 objects are in contact, the heat Scientists commonly use 2 equivalent units of temperature: the Celsius scale, which sets the freezing point of water to 0 degrees Celsius, and the boiling point of water to 100 degrees Celsius. And scientists commonly use 2 equivalent units of temperature: the Kelvin scale, after Lord Kelvin, who was a Scottish physicist, that sets the freezing point of water at 273 Kelvin, and the boiling point is 373 Kelvin. So just 100-degree difference in Kelvin between the freezing and boiling point of water. Scientists use these 2 scales, Kelvin and Celsius, as you can see here. And you can see here, they're both a 100 division difference. So between the freezing and boiling point of water on the Celsius scale, there's a 100-degree difference, or 100 division difference. And the same goes for the freezing point and boiling point of water on the Kelvin scale. Between 273 and 373, there's a 100 division difference. The 0 point on the Kelvin scale, 0 degrees Kelvin, is absolute 0, and that is equal to negative 273 Celsius. And we can use this conversion then pretty easily, going from Kelvin to Celsius. Kelvin would equal the degrees in Celsius. plus 273, and Celsius would equal the degrees in Kelvin minus 2. Okay, sorry for all the interruptions. I've had to pause and stop the recording for a couple of different reasons. Converting then between temperature scales, let's do a sample problem. Normal human body temperature is 37 degrees Celsius. What temperature is this temperature in Kelvin? So let's list the knowns and unknowns. The known value and the equation is Kelvin equals Celsius plus 273 to calculate the temperature in kelvins. We're given the temperature in Celsius, 37, and we need to know the temperature in kelvins. So we just use our simple equation by substituting the known value for the Celsius temperature into the equation and solve. So Kelvin equals 37 plus 273. So our answer is Kelvin in 310 Kelvin. All right, so moving on, we have to evaluate the sample problem, and that does make sense. You should expect the temperature in this range since the freezing point of water is 273 and the boiling point of water is 373. So normal body temperature would be somewhere in between those two values. All right, density then is the ratio of the mass of an object to its volume, and this relationship will determine if an object will sink or float. Density units, when mass is measured in grams and the volume is measured in cubic centimeters, we get the density units are grams per cubic centimeter, and the SI unit of density is actually kilograms per meter cubed. Increasing density mass per volume, if we take lithium versus water, aluminum, and lead, lead is more dense, taking mass per volume, as you can see there. And the figures show the comparisons of density of those four substances. A little more on density. It's an intensive property that depends only on the composition of a substance, not the actual size of this sample. Because of differences in density, liquids can actually layer. So if we were to do this kind of as a little experiment, taking corn oil, water, and corn syrup, the denser liquid would sink to the bottom. That's the corn syrup, and the water and the corn oil would float to the top as the less dense liquid. If temperature increases, the volume will increase as the temperature increases while the mass remains the same. That's one kind of property we get. So as temperature increases, the density will decrease. Let's do a sample problem. A copper penny has a mass of 3.1 grams and a volume of 0.35 centimeters cubed. What is the density of the copper? We have to remember that density equals mass divided by volume. Let's list our knowns and unknowns. We know the mass, we know the volume, and we need to solve for density. So really simply put, our density will be measured in grams per centimeters cubed. So we just need to divide the mass divided by the volume to get our density, and we'll see if that makes sense. So for the density, we will get 8.8571, rounding it to significant figures of two significant figures because that's what our problem is in. We get 8.9 grams per centimeter cubed. Does the result make sense? A piece of copper with a volume of about 0.3 centimeters cubed has a mass of about 3 grams, and about 3 times that volume of copper should have a mass about 3 times larger, about 9 grams. So this estimate is actually close to our estimated value. Thanks for listening to this section, guys, and take a look at the extra video that I post that helps explain some of these conversion units, and take care. I hope you guys are doing well.